Hello, and welcome to the video for the KC1 final review. Let's get started. Number 1. David rode his bike to the park. After staying at the park for a while, he continued his ride to the grocery store. The graph shown represents this situation. A. Identify the domain and the range. Now let's remind ourselves. Our domain is our set of x's. So that's going to be our x-axis, so that's the horizontal, left to right. Our range, we'll be talking about our y's. So our y-axis, that goes from the bottom to the top. So let's check it out. Our domain. I'm going to start on the leftmost part of our graph, and I'm labeling that with an L. I'm going to put my pen on it, and it seems that all the way to the left, the number that I'm starting at is 0. So I'm going to place a 0 right there. Now I'm going to trace my graph until I get to the rightmost part of it, until it ends on the right. So let's see. I'm going, it ends right here. So that means we're going from 0 to 50. Next, let's do our range. Our range, on the other hand, goes from the bottom, which happens to be at the same location, all the way to wherever our graph ends on the top. So on the very bottom of our graph, we're starting at 0 as well. I'm going to trace my graph all the way to the topmost part of it, and I'll see where that ends. Okay, and it seems to end right here, so that's my top. Directly between 2 and 3, we have 2.5 for our range. Perfect. Now let's check out letter B. Is the graph increasing, decreasing, both increasing and decreasing, or constant? Explain your reasoning. So the way I'm going to do it is I'm going to state when it's increasing and when it's decreasing, when it's constant, and tell the intervals. All right, so I'm going to begin on the right-hand side. And let's use this color. I'm going to put on the right. I meant to say on the left-hand side. My bad. I'm going to start on the left, and I'm going to trace my pen and see what's happening to my graph. Now, as I trace it, this little area here, it looks like it's going up, which means increasing. Now let's see, what is the interval that I'm increasing from? Well, I start at 0, and I go all the way down till, well, between 10 and 20 is 15. Perfect. Let's see what happens next on my graph. I'm changing colors because it looks like it's not going to go up again. Check it out. This time, it's going straight across. This is called constant. My graph is constant from that 15 where I ended increasing all the way through till 40. Now what's happening to my graph after 40? After 40, my graph continues to increase. So I'm going to add in this interval and from 40 all the way through, I don't know why I wrote a 4 again. I meant to write through 50. There we go. Now the way you write this varies. I've had some students write full sentences or just use different notation. Maybe just write an I for increasing and a C for constant. But I do need those intervals. So that the explaining your reasoning is giving me the intervals. All right, so however you tell me that it's increasing from 0 to 15 and then from 40 to 50, that it's constant from 15 to 40. Let's try all of that again. All right, in this problem number 2, Juanita and her friends went on a hiking trip. They hiked a mountain trail, stopped to eat lunch, and continued towards the summit of the mountain. The graph represents this situation. Once again, let's identify the domain and the range. The domain is the x's, and the range is the y's. So let's check it out. My graph over here on the very left, it starts at 0. And I'm going to trace my graph and see where it ends. It ends all the way over here at 200. So we're going from 0 to 200. Okay, now let's see what our range is like. Our range is our set of y's, and the y's go from the bottom to the top. Well, let's see where our graph starts. our graph starts right here. It actually starts at 500. And I trace my graph all the way to the top of the line, and it seems like I end at 2000. So that's my range. Next, let's talk about our constant increasing, decreasing intervals. Once again, I'm going to trace my line. I'm going to start at the leftmost area, and then I'm going to trace and see what's happening. It seems like right here, I'm increasing because I'm going up. So I am increasing, and we're going from left to right. So from 0 through 80. Perfect. Let's see what happens next. Next, it looks like I'm going just straight across. It's flat, and that ends at 120. When it's flat like that, that's called constant. And I'm constant from the 80 at which we stopped increasing all the way through 120. Let's check out what happens next. Next, from that 120, it seems like I'm increasing to the very end. So that's 200. So I'm increasing also from 120 through 200. Again, you can write full sentences however you tell me that it's increasing from 0 to 80 and 120 to 200, and then it's constant from 80 to 120. However you explain that to me, I need to see those intervals, and I need to see the words increasing and constant, or maybe an I to represent increasing or a C to represent constant. All right, onwards we go. For questions 3 through 7, I'd like us to determine whether or not each relationship represents a function, and we're going to explain why. All right, let's start with number 3. Number 3 is a graph. When we have a graph, the way we determine whether or not it's a function is by using the vertical line test. This is what the vertical line test is. If I draw a vertical line, meaning straight line going up and down, through the shape of my graph, I should only cross the graph once if it's a function. If it crosses more than once, it's not a function. So let's see. I drew my orange line, and I want to see how many times did it cross that U shape. My orange line crossed once, it crossed twice, so no, not a function. Fails vertical line test. All right, number 4. Number 4 is a table. When we have a table, what we're looking at is to make sure that our x's do not repeat. Our y's can repeat as often as they can. So let's see, in number 4, all of my x's are different. Now I know it's tempting for some of us to think that 2 and negative 2 are the same number, but they are opposites. One is a positive 2, the other one is a negative 2. They are not the same number. So number 4, yes, it's a function. X's don't repeat. Number 5 is a map. On a map, what we're looking for is to make sure that each domain only goes to one range. And in number 5, that happens. Every number from the domain only has one arrow coming out of it to one range. So, yes, each domain only goes to one range. Number 6 is a table again. Let's make sure our x's don't repeat. Now I do see a negative 5 and a positive 5, but luckily for us, those are two different numbers. And you may notice that in our y's we have two 25s, but you know what? Who cares? As long as the x's don't repeat, it's a function. So yes, x's don't repeat. Number 7 is another map. Now in number 7, I see one of my domains going to two different ranges. Check it out. That 0 has two arrows coming out of it. it should only be going to one range. So the answer here, no. One of the domains goes to two ranges. All right, let's continue. Number 8, consider the sequence shown. And the sequence is this pattern that we're seeing with the little blocks. Describe the pattern. Well, let's see. The first set of blocks we have is 3 blocks. The second set has 5, and the third one has 7. So to describe this pattern, I could say it increases, or just increasing, by 2 blocks, or squares. I don't know why I thought blocks. They could be squares, rectangles, whatever you want to call them. Write a numeric sequence to represent the first 5 figures. Well, I have the first 3 figures. It's 3, 5, 7. Now our pattern, like I said, is increasing by 2, which means I'm adding 2 each time. So let's add 2 more. 9 and 11. So there's my first 5 terms. Let's find the 10th number. What I'm going to do is just keep going with that pattern. So that's the 1, 2, 3, 4, 5. I have 5 terms. Let's do 5 more. So after 11, we have 13, then 15, then 17, then 19, and our 10th term, 21. All right. Number 9. Write the first 5 terms of an arithmetic sequence with a common difference of negative 2.2 and the first term of 0.2. Well, let's see. Our first term is 0.2, which means I'm going to write 0.2 right there. Our common difference is minus 2.2. So that is the pattern that we're going to be following. So I'm going to subtract 2.2. When I do 0.2 minus 2.2, I get negative 2. Subtract 2.2 again. I get negative 4.2. I subtract again. And again. And there are our first 5 terms. Let's do that again for number 10 and 11. All right, so first let's find our first term. Write the first 5 terms of the arithmetic sequence with a common difference of minus 0.4 and a first term of 0.7. There we go. Our arithmetic sequence has a common difference of minus 0.4. So that's what we're going to subtract each time. So 0.7 minus 0.4 is 0.3. Then I'm going to subtract again. I get negative 0.1. This is a little thicker than I wanted. There we go. Subtract one more time. Negative 0.5. And one last time. Negative 0.9. All right, onwards to 11. Write the first 5 terms of an arithmetic sequence that has a common difference of negative 0.25 and a first term of 5. So our first term is 5. Let's write that down as our first term. Our common difference is minus 2.5. Let's begin subtracting that to find our next term. All right, let's do it. 5 minus 0.25 is 4.75. I subtract again. I subtract again. And one last time. For questions 12 through 15, identify each sequence as an arithmetic or geometric sequence. Then determine the common difference or the common ratio for each sequence. Number 12. So first we need to decide whether or not it's arithmetic or geometric. So when I'm looking at this sequence 48, 12, 3, 0.75, and then 0.1785, these are pretty large jumps in my numbers. So I'm going to say it's a geometric sequence. So arithmetic sequences are sequences that go by addition and subtraction. Geometric sequences go by multiplication or division. Generally, when there's big jumps in numbers like that, I like to test out geometric first. All right, let's see. If I do 48 divided by 12, I get 4. If I do 12 divided by 3, I get 4. 3 divided by 0.75 is 4. 0.75 divided by 0.1785 is also 4. Awesome. So we actually have a common ratio. We're dividing by 4, or the more common way of writing it is that we're multiplying by 1/4. All right, let's check out number 8. Number 13. Here it looks like the jumps in my numbers are pretty small, so I'm going to say it's arithmetic. To get from 8 to 11, if it's arithmetic, I would be adding 3, right? 8 plus 3 is 11. 11 plus 3 is 14. 14 plus 3 is 17. And 17 plus 3 is 20. So yes, it is arithmetic. That means it has a common difference. We're adding 3 each time. I'm going to rewrite that 3. That wasn't that pretty. Okay. Next, number 14. From 5 to 3.5 to 2 to 0.5. I think this is arithmetic. Let's check it out. To get from 5 to 3.5, if this was arithmetic, I would have to subtract 2.5. No, 1.5. 1.5. Yes, 1.5. To get from 3.5 to 2, I would also have to subtract 1.5. I am right. This is arithmetic. We have a common difference. We're subtracting 1.5. All right, number 15. Oh, that's a pretty big jump from 1 to 6, 6 to 36. Look at how large these numbers are getting. I'm going to guess that it's geometric. So geometric is multiplication and division. So if I was going to get from 1 to 6 by multiplication or division, I would have to multiply by 6. To get from 6 to 36, times 6, times 6, times 6. All right, we have a common ratio of times 6. 16. From the following sequence, write the explicit formula, or write an explicit formula. So in our explicit formulas, A1 represents our first term, and D represents our pattern, our common difference. N would be the number of the term we're looking for, but we're just writing the formula. All right, so A1, our first term, is 12.6. So A sub n equals 12.6. D is our common difference. Now we know this is a sequence, it already said that. So let's see. The way I'm going to find my common difference is I'm going to do 12.6 minus 5.6, because I'm thinking, how am I going to get from 12.6 to 5.6? And it looks like I'm subtracting 7 each time. So 12.6 minus 7 is 5.6, minus 7, this works beautifully. So I put a minus 7 for D, our common difference, and then parentheses next to it, and minus 1. Let's try that again. A1 is our first term, D is our common difference. So first term is 10.2. Our common difference, all right. So another way of thinking about it, rather than writing down the subtraction like I did in the last problem, is how do I get from 10 to 2.2? Well, I'd have to subtract. 10 minus what gives me 2.2? 10.2 minus what? Well, 10.2 minus 8 gives me 2.2. And if I keep subtracting, I'll get the next terms. So, minus 8, and then an n minus 1 next to it. For number 18 and 19, we're going to be actually writing a simpler one, a recursive formula. In the recursive formula, we're using the term before it to find the next term. So all we're looking for here is D, our common difference. So the first thing I'm going to do is rewrite this a sub n minus 1. My common difference is how I get from the first term to the next. Now, to get from negative 20 to negative 9, and from negative 9 to 2, from 2 to 13, I have to add 11. That's it. That's our formula. Let's do that again to number 19. The first thing I'm doing is just rewriting a sub n minus 1 because that just means we're using the previous term plus the common difference to find the next term. All right. So to get from negative 25 to negative 12 to 1 to 14 to 27, we are adding 13 each time. That's it. Onwards we go. Let's determine the 20th term of the sequence defined by a sub n equals 2 plus 3n minus 1. All right, so if I'm looking oh, I zoomed out too much. Come back. There you are. Okay, I'll be gentler this time. Okay, so our 20th term means we're going to be taking this 20 and plugging it in to our formula, or I guess the sequence that we have defined over here. So I'm going to rewrite this as 2 plus 3 parentheses 20 minus 1. Now, sure, you can plot this all into your calculator as one kind of sentence and get your answer, but I'm just going to show it to you step by step. The first thing that I'm going to do is subtract what's inside those parentheses. 20 minus 1 is 19. Now that I've done that, I can multiply now. I'm going to multiply 3 times 19. 3 times 19 is 57. 2 plus 57 is 59. So my 20th term is 59. Number 21 asks us to determine the 25th term defined by that sequence. So let's plug it in. Oh, that didn't switch over to my pencil. That was funny. All right, let's erase that. There we go. Okay. So 8 plus 2, parentheses, 25 minus 1. Like I said in the previous problem, you can plug this into your calculator. I'm going to show you step by hand. So the first thing that I'm doing is subtracting inside my parentheses. Then I'm multiplying. And 8 plus 48 gives me 56, which is the answer to 21. All right, last two problems. Let's do it. When first purchased, a tree sapling measures 3 centimeters tall. Every month thereafter, the sapling grows 2 centimeters in size. Let's represent the height of the sapling in centimeters over the first five months. Okay, so when first purchased, the tree sapling measures 3 centimeters tall. So I'm going to put a 3 right here in 1, under the 1. Every month, the sapling grows 2 centimeters. So that means between the first and second month, second and third, third and fourth and fifth, the tree increases by 2 centimeters. So let's do some addition. 3 plus 2 is 5, plus 2 is 7, plus 4 is 9. What? Plus 2 is 9, plus 2 is 11. I think I looked at that 4 and said plus 4 instead. Write the explicit or recursive formula. I'm going to write the explicit formula. The explicit formula looks as such. First, we write down the first term, then our common difference, and then n minus 1. Predict the height after 8 months. All right, no problem. Explaining your reasoning here means showing your work. So what I'm going to do is I'm going to take that 8 and I'm going to plug it in to our formula that we wrote in part B. Let's solve it. This becomes 3 plus 2 times 7. Then we multiply. Then we add. So 17 centimeters is going to be the height of our sapling after 8 months. Lastly, number 23. When first purchased, a tomato plant measures 2 centimeters tall. Every week thereafter, the plant grows 5 centimeters in size. Let's represent the height of the plant in centimeters over the first 5 weeks. Okay, so our tomato plant begins at 2 centimeters. So 2 centimeters goes under 1. It grows 5 centimeters every week. So that means between the first and second, second and third, third and fourth, fourth and fifth, we're increasing by 5 centimeters. So let's do some adding. 2 plus 5 is 7, plus 5 is 12, plus 5 is 17, plus 5 is 22. I'm going to write the explicit formula for letter B. I prefer that one. So we begin with the first term, then our common difference, and then n minus 1. Let's predict the height after 9 weeks. Explain your reasoning. Explaining our reasoning means showing our work, so let's do it. What we're going to begin by doing is plugging the 9 into n from our previous part of our problem in our explicit formula. Okay. First, I'm going to subtract inside those parentheses. 9 minus 1 gives us 8. 5 times 8 is 40. And then, of course, I finish by adding. 2 plus 40 is 42. So 42 centimeters after 9 weeks. All right. So I hope going through this with me out loud was helpful for you. And I hope this is helpful in you studying for the final. If you have any questions, please don't hesitate to ask myself, or if you are someone else's student, don't forget to ask your teacher. Have a wonderful rest of whatever day it is for you. Bye.